Hi, this is the module number 14. Here we are going to see how to perform an hypothesis test that is called one-way ANOVA. This hypothesis test, it has the same structure as the previous hypothesis test we have seen before. What is that structure? Set up the hypothesis. What are the hypotheses here? In ANOVA, the hypothesis is what? All the means from several populations, from K populations, they are the same. The alternative, at least one of the means is different. And notice how I say at least one, because maybe all of them can be different, or maybe only a few of them. But if at least one is different, so we have that satisfy the alternative hypothesis. State the level of significance. The test statistic here, the test statistic is going to be computed by using the F distribution, and the test statistic is going to be denoted by F subscript observed. Well, actually, in the homework from Achieve is only denoted by F, but sometimes that can be confusing because F is also representing the F distribution, a random variable with the F distribution, and also one value for that distribution. But well, here I prefer to say F observed, the particular value for the test statistic. Then we're going to compute the p-value by using probability that F is greater than F observed. I mean, the probability that the F distribution is greater than the value we got here. Yeah. And then the rule that we already know, reject H0 if what? If the p-value is less than the level of significance. And again, notice how this is the same structure we have seen before for all the hypothesis tests we have seen in this class. All right, so this is the introduction for this. Now let's see the examples. Of course, as we are seeing the examples, I'm going to be explaining more things, right? For example, how to compute the statistic, some assumption we have to make, and in general, the main assumption we have to make, but usually we don't deal with that here when we are doing these exercises, is that all of these are from population with a normal distribution. That is the main assumption that we have to make. But well, let's see some examples. All right, the first example. Suppose a horticulturist measure the above ground height growth rate of 4 different. Here we have some information. 4 different. So it seems like we are going to be having here 4 populations or 4 categories. Ornamental shrub species grown in a greenhouse. The shrubs were grown from a random sample of seeds, and they were all grown in the same soil mixture and in the same size pot. To ensure that any slight differences in the environmental conditions throughout the greenhouse are not confounded with the species, she randomizes the location of the pots throughout the greenhouse. The table contains a summary of her data. And there you have. This is the data that we have. Notice, as I have said before, we're going to be comparing here populations. Here, population 1, population 2, 3, 4. We have 3 populations, and all of them, they are representing several species. When we have an ANOVA test, or we are performing an hypothesis test with ANOVA, we are going to have the mean. Well, we will need to compute the mean from each sample. But in this case, notice that we have sample for each population. In this case is 20, 20, 20 for all of them. Here we have the standard deviation. I mean, this is the mean, and these are the standard deviation. So this is typical that it has to do with ANOVA, okay? After that, something that is strongly related to this kind of test is the next table. Is this table you see here? It's a table for ANOVA. Typically, you're going to be seeing this table, and you will have to know how to interpret it. So, well, first, notice we have all the steps to compute this. I'm not doing here all the steps by hand, all right? Rather, I will explain how to compute it by using Minitab. But we're going to be seeing how to use, for example, the how to compute the degrees of freedom. We will see that for other examples later. This, the mean square error between the groups or within the groups, the p-value, and the value for the f observed will be this one. And notice the p-value. So we already have this here. In this example, we don't have to compute anything. Only we are given this. What are the hypotheses? So complete the sentence to state the decision and conclusion of the horticulturist test. So here, what are we talking about? Species, right? So H0 would be species 1 is equal to species 2, species 3, species 4. The alternative, at least one different. Yeah, I know. Notice, remember this mu is representing the mean from the population, and this x bar is representing the mean from the sample. We observe obviously that from the sample, from the given size, each mean is different, right? But is that evidence enough to conclude that in general from the population they are different? So that's why we perform an ANOVA test. So in this case, what do we have to do? We already have the p-value. So what is the level of significance? So it's this one here. Do we have to reject or not? Remember, if the p-value is less than the level of significance, reject H0. So in this case, you will have to respond this from a bank of answers. So here, the decision is to reject the null hypothesis at a significant level of 0.04. There is sufficient evidence to conclude that. Notice, if we are rejecting the null hypothesis, we are saying that the evidence goes in favor that not all the means are equal. So there is at least one difference. At least one population mean is different from at least one other population. I mean, of course you don't have to write this. I mean, you're going to see the answer from a given box. So let's continue. Degrees of freedom. Something related to this kind of ANOVA test is going to be, you will have to compute the degrees of freedom. I'm going to explain here how to compute the degrees of freedom. Suppose the example says, suppose that Ron recently opened a candy shop selling his newly crafted chocolate candy, Ron Runs. Due to the surge in popularity of Ron Runs, Ron hires several employees to take orders over the phone because of the large influx of calls from candy craving customers. Callers are often placed on hold for several minutes. After a few hours, customers begin to complain about the lack of hold music as an indication that they're still on the line with Ron's candy store. Ron wishes to determine if different genres of hold music entice customers to purchase differing amounts of Ron Runs. Over the few days, Ron decides to randomly select 134 customers. So notice this is like the total amount of samples from the populations. Customers to be placed on hold immediately upon calling. He then randomly selects one of three genres of music: rock, country, or rap, to be played to the customer. He then records the quantity of Ron Runs purchased by that customer. The ANOVA table shows the results of Ron's study, the between groups, within groups, and total degrees of freedom denoted by DF1, DF2, and DF total respectively are all missing from the table. All right, so we have to compute this. First, N is going to be the total number of elements in the sample, for all the samples, all right? So in this case, it's going to be 134. Then you will have to know the number of categories. The categories, usually they are denoted by K or the different populations. In this case, we have only three genres: rock, country, and rap. Three. Now with this, the degrees of freedom 1 is computed by using K minus 1. In this case will be 3 minus 1 equal to 2. And degrees of freedom 2 is N minus K equal to 134 minus 3, that is 131. 2 and 131. By the way, I think this problem is not asking for this, but how do we compute the degrees of freedom total? Do we have to add these two? Yeah. Degrees of freedom total is 2 plus 131. All right. And that's all what you have to do here. DF1 is 2, and DF2 is 131. That's all for this exercise. Another example, determine F from MSE. MSE is a concept from ANOVA. It means mean square error. It says, suppose a team of doctors wanted to study the effect of different types of exercise on reducing body fat percentage in adult women. The 38 participants in the study consist of women between the ages of 40 and 49 with body fat percentages ranging from 34% to 36%. The participants were each randomly assigned to one of 4 exercise regimens. So notice here we already have, again, the indication like for the number of population, or well, in the ANOVA test, we also call them treatments sometimes. Well, many times, most of the times actually. So we have 4 exercise regimens. So 11 were instructed to complete 45 minutes of aerobic exercise. 10 were instructed to complete 45 minutes of anaerobic exercise. 10 were instructed to complete 45 minutes, and 7 were instructed not to exercise at all. All participants were asked to adhere to their assigned exercise regimen for 8 weeks. Additionally, to control for the effect of diet on weight loss, the doctors provided the participant with all meals for the duration of the study. After 8 weeks, the doctors recorded the change in body fat percentage for each of the participants. So, what are we testing here? What method of these 4 exercise regimens whether they are the same or not. So in this case, the null hypothesis would be H0, mu1, mu2 equal to mu3 equal to mu4. Yeah? So this is all the regimens, the 4 regimens, do they work in the same way? That is the null hypothesis. And how do we measure that? It says the control after 8 weeks, the doctors recorded the change in body fat percentage. So if the change was the same or more or less the same, then that means that the 4 regimens they don't make any difference, right? But if they're not the same, then at least one of them is going to be better than the other ones. So the doctors plan to use. Oh, I'm sorry. This is alternative. At least one different. The doctors plan to use the change in body fat percentage data in a one-way ANOVA test. They calculate the mean square for groups as MSG equal to this. All right. This is other value typical from ANOVA when you are computing this by hand. What is the meaning for each? MSG, mean square from groups. MSE, mean square from error. For example, in the first case we saw here, that information was provided here. You see this MS. So in this case, in our example, these values are given. How to compute this? Well, there is an operation that we have to do. I don't go over them here. Yeah, I recommend that you want to know the details as to how to compute this from the raw data. I recommend to read the book, or if you want to ask me by email or go to the virtual office hours, or go to the office hours or set up a meeting for the virtual office hours, no problem. But I won't explain how to compute those values here. We are going to compute all of this later with another example by using Minitab, but not to compute them manually, So in this case, this is going to be 10.899112 and 1.534706. There you have. So we're going to need this. How do we compute the F statistic with this? The F observed is MSG over MSE. So in this case it will be 10.899112 divided by 1.534706. If you do that, the value you're going to get is 7.0436. You can verify that in your calculator. So now what you have to do in this exercise after computing this is choose all the facts about the F statistic for the doctor's ANOVA test. First, the F statistic is 7.0436. Yeah, that is true. The other ones are the F statistics increases as the differences among the sample means for the exercises groups increase. That is true. And the degrees of freedom 1, they are also called, by the way, degrees of freedom from the numerator. And in this case, it's equal to what? How do we compute this? Is number of categories. In this case, we have 4 types of exercises. So it's going to be 4 minus 1, that is 3. And the degrees of freedom 2, that is also called degrees of freedom from denominator, is the total number of values that is 38 participants minus the number of categories. 38 minus 4, 34. You see? So in this case, the answer is going to be this one. 3 degrees of freedom numerator, 34 in the denominator. Again, degrees of freedom 1 is number of categories minus 1. Degrees of freedom 2, total number of observation from the sample minus number of categories. Next, run ANOVA test. Using software, conduct a one-way analysis of variance, ANOVA F test at a significance level of 0.025. To determine if the mean weight for Hispanic men of age 22 to 34 for 4 regions. So again, notice 4 regions, so that means we're going to have 4 categories of the country are all equal. Sample data collected for Hispanic men of age 22 to 34 is provided by US region in the data file. In the Excel, all right, this we don't need to read out after that. So you will have to download the data here, and of course, go to Minitab to do this. Go to Minitab. You go to File, Open, Worksheet, Local File, OK. This, again, this is fine in the given exercise on a chip. Yeah? Open it. And there you have information about the weight for Hispanic people in the United States from 4 regions. All right, now how to perform an ANOVA test. So, right, you will have to go to Stat Basic Statistics. Oh, no, I'm sorry, Stat ANOVA. You see, there is the option immediately. One-way ANOVA. And then in the response, of course, it's going to be BMI. The factors are the treatments or the categories. In this case, it's the region. Then options, I think we don't have to choose this by now, assuming covariances, all of that, leave it like that. That okay? I think you don't have to touch the options. In the option by default, I think they're going to be correct. So, okay, that's all, you see? Continue without autosave. And notice, you're going to be given a table like the one we have seen before, only by doing this, you see? So it's very simple to compute the analysis variance by, if you have the data, the raw data, right? So this analysis variance, notice how we have the f-value, the p-value, and actually you have the degrees of freedom, right? In this case, 3 and 600. And so the mean square error from the groups or region in this case, and from the error, all right. But what do we need here? We need the f-value and the p-value. So the degrees of freedom what is asking for the exercise is asking for degrees of freedom 1, degrees of freedom from the numerator. Degrees of freedom from the numerator is 3. Degrees of freedom from the denominator, this one you see, 600. The F statistic is, you can see it here, F value 1.75. And the p-value, by now, it is computed in the table. In one example later, we're going to see how to compute it by, we have only the F observed, is 0.157, so it's given here. So what are the decisions? P-value is not less than alpha, right? The value for alpha, we have to use it this one, you see? 0.025. So the p-value is 0.157, so it is not less. It is not less. So we what? We don't reject. We don't reject H0. So it seems what? We are assuming here that what is H0 in this case? The mean weight from mu1, mu2, mu3 equal to mu4. Mu1, mean weight from region 1, and so on. Mu4 is mean weight from region 2, region 4. What are the regions, by the way? I think the regions are given here in Minitab. You see? I think Northeast. You want to be more specific about this, there you have. But we have 4 regions. So the point is that we have 4 regions, and the means from the 4 regions, they are supposed to be equal. We are not rejecting that. So no evidence to say they are different, right? No evidence to say they are different. So here we have to write fail to reject. Because the p-value is greater than there is insufficient evidence that one or more of the mean weights for Hispanic men of age 22-34 are different. So this is what you have to write here. One more example, little bird. The males of many animal species signal their fitness to females by displays of various kinds. For male barn swallows, the signal is the color of their plumage. Does better color really lead to more offspring? So again, notice even when they're talking about technical issues, right? And maybe, of course, I don't understand completely. As for the problems, not the concepts related to statistics, right? The context from the problems. They can be very technical sometimes, right? From other fields that they are not statistics, of course. Maybe they are not from your field either, but try to look for to identify what we are talking about here. So does better color really lead to more offspring? A randomized competitive experiment assigned barn swallow pairs who had already produced a clutch of eggs to three groups. So notice three groups. 13 males had their color enhanced by the investigators. 13, 9 were handed, but their color was left alone, and 8 were not touched. So we have three categories or three populations, right? DNA testing showed whether the eggs were sired by the male of the pair or by another male. The investigator then removed the eggs. Barn swallows usually produce a second brood if the first one failed. The male with enhanced color fathered more young in the second brood, and the males in the other groups fathered fewer. The investigators used ANOVA to compare the three groups. So here in this case, is what are the degrees of freedom from numerator and degrees of freedom from the denominator of the statistic. All right. First, degrees of freedom 1, remember, is the number of categories minus 1. So we have k minus 1. We have 3 categories. Yeah. 3 groups. This one here. Yeah. 3 categories. So it's going to be 3 minus 1. 2. Degrees of freedom 2 is total number of observations. So in this case, we have to add, right? We have the total number of observation from the samples. They were 13 plus 9, 22 plus 8, 30. So n minus k, that is 30 minus 3 equal to 27. So 2, 27. Notice here we are given the statistic. The statistic was this one. What can you say about the p-value? Notice how we don't have the raw data, so we cannot perform the analysis of Minitab because we don't have the raw data. But anyway, the p-value, if you have the test statistic, p-value is probability that the F distribution is greater than F observed. In this case, probability that F distribution is greater than 0.07. It's a very low value. I think we are not rejecting the null hypothesis. Anyway, we need to compute this. All right. To compute the p-value, you are going to need the degrees of freedom. The degrees of freedom, in this case, from the numerator and from the denominator, they are 2 and 27. From numerator, denominator. So we have to use Minitab, of course. Go to Minitab. Then I think that's what here, probability distributions. Do we have to use cumulative distribution function? Should the F, notice you see, so you're going to see only a capital F. And it depends on two parameters, degrees of freedom numerator, the denominator. So they are, in our case, 2 and 27, 2, 27. What is the value for the test statistics? 0.07. And I think that's all. Okay. The table is going to give you, the Minitab is going to give you the probability that F is less or equal than F observed. So notice the table, Minitab gave me the probability. I'm looking for the probability that F is greater than 0.07, but Minitab with that outcome gave me the probability that F is less or equal than 0.07. How do I compute what I want? Subtract that from 1. 1 minus the result from Minitab, and you're going to have the answer. The answer is going to be 0.9325. And then, so do we reject the null hypothesis or not? It doesn't say the level of significance, right? So remember, if it doesn't say, use alpha equal to 0.05. Alpha equal to 0.05, so what is the right option? I think it's the first one. The value is 0.07, the p-value is greater than 0.10. So we don't reject H null. We don't reject H null. So the evidence goes in favor that the means maybe are equal, that the means are equal. So no difference to conclude they are different. So I think it's the first one. With F equal to 0.07, the p-value is greater than 0.10. Notice how it doesn't say the exact value. We conclude that there was no difference among the groups. The means are the same in the number of young in the first brood. In other words, the random allocation to the three groups worked. No group produced a significantly different number of offspring in the first brood. Now, in the same problem, what happened with the second brood? 27 produced a second brood. So here the degrees of freedom, the number of categories, they don't change. So it's going to be 2. But for degrees of freedom 2, we have, it's going to be n minus k. In this case, we have 27 minus 27 minus 3, yeah, I'm sorry. 27 minus 3, yeah, because we had 3 categories. Yeah, okay, it's 3. So 27 minus 3 is going to be 24. So in this case, this changed to 24. Now here, the statistics change to 5.45. What can you say about the p-value? So how to compute it? The same. P-value is equal to the probability that F is greater than 5.45. equal to 1 minus the probability that f is less or equal than 5.45, and this is provided by Minitab. Go to Minitab, be careful, be sure that you change the degrees of freedom. Calc, probability distributions, cumulative. Now the f value is 5.45. F, the degrees of freedom, now we have 2 and 24. And then, okay, notice the probability is 0.98838. So 1 minus 0.9888. And this is going to be 0.0112. So p-value is 0.0112. There you have. So what do we reject H null here? Since p-value is less than alpha equal to 0.05, yes, we reject H null. We reject H null. So in this case, the means are not the same. We can say that we have evidence to say that the means are different. So the right option here is we have sufficient evidence that at least one mean second minus first count is different. So I think the option is this one, the second one. P-value between 0.01 and 0.025, that is correct. And we reject H null. So at least 1 minute difference. Caffeine and sugar. Next example. A double-blind random experiment assigned healthy undergraduate students to drink 1 of 4. So notice here, so maybe there we have 4 categories. Beverages after fasting overnight. Water with 75 milligrams of caffeine, water with 70 grams of glucose, and water with 75 milligrams of caffeine and 75 of glucose. Subjects perform a number of cognitive tasks, including the California Computerized Assessment Package, a computerized reaction time program measuring sustained attention, reaction time, and visual scan and speed. The table contains the resulting reaction time and the standard error of the mean. And there you have this number of samples and this. What is the population here? It's going to be this one. All healthy undergraduate students who drank 1 of 4 beverages before completing the task. So what is the response variable? The response variable is, what are we measuring here? Table contains the resulting reaction time. So reaction time. What are the degrees of freedom? Degrees of freedom from numerator, or degrees of freedom 1, is number of categories. We have 4 categories minus 1, so it's 3. And from denominator or degrees of freedom 2 is the total number from the sample. So multiply 18 times 4 is 72, right? So all the observations from the sample, they were 72. So 72 minus number of categories, so 68. 3 and 68. And I think that's all for this exercise. Yeah. One more example from a sheet, bromeliads. Bromeliads are tropical flowering plants. Many are epiphytes that attach to trees and obtain moisture and nutrients from air and rain. Their leaf bases form caps that collect water and are home to the larvae of many insects. As a preliminary to study of changes in the nutrient cycle, Jacqueline and Guy and Diane Strisbasta examined the effects of adding nitrogen, phosphorus, or both to the cups. They randomly assigned 8 bromeliads growing in Costa Rica to each of 4 treatment groups. So here we have 4 categories, including an unfertilized control group. So a monkey destroyed one of the plants in the control group, leaving 7 bromeliads in that group. The number of new leaves on each plant over the 7 months following fertilization are contained in the table. State how does the presence of nitrogen, phosphorus, or both affect the development of new leaf-seam bromeliads. So we are assuming that they are the same, the means are the same. Examine the data to compare the effect of the treatments and check that we can safely use ANOVA. Use the software. Oh, here you need to download this from the. You need to upload this into Minitab. The file is given in the exercise. So go to File, Open, Worksheet. I have it in my computer. Local file is bromeliads. I named this as bromeliads. Open, and there you have. You see? So here first in the exercise said that you have to compute the stem plot. Remember, I think we saw stem plots in the first chapter from this. I think module number 3. But how do we compute the stem plot? Right, stem plot is the graph. Go to graph, stem and leaf plot. Oh, but we have a problem with this template. You know, here, unfortunately, here in Minitab, in this version of Minitab, we cannot compute the 4 stem plots together. So what can we do in that case? Well, I use something to solve this. First, notice we have 4 categories: neither, nitrogen, phosphorus, and both. So I'm going to label each of those outcomes with one number from 1 up to 4, 1 for neither, 2 for nitrogen. And well, actually it doesn't matter what is the number 1 or 2 or 3 or 4, right? The point is that each of them has to be different. So 1 for neither, but first I need to create a new column with that labels. So I did it in calculator. So notice, it is given here, you see that? So what am I doing this? Do we have to use first the if function? So again, let me repeat this. Go to calc, calculator. You're going to choose the if function, double click. You will have it here. Store results in C3. And then you are going to put the labels for each of the outcomes, right? Nitrogen is going to be labeled as 1, phosphorus as 2, both as 3, and neither as 4. We have to copy this, okay? There you have it. You will have to put this little code. 1, and then put the results in C3. Once you have done this, Okay. And notice in the column 3, we're going to have for each outcome of neither phosphorus, both, or nitrogen, we're going to have 1, 2, 3, or 4. Now, once you have this, go to graph, stem and leaf plot. Y variable is going to be new leaves. Group variable should be column 3. And with that, we're going to have the 4 stem plots together. There you have. You see the stem plot, for 2, for 3, and for 4, or neither. There you have. So with this, you can respond to this, select the best response. The right response is side-by-side stem plots show some irregularity, but no outliers or strong skewments, right? So I think the main point with this is that we observe that we don't have many outliers, or that the distribution that you see here for the stem plots, they are approximately normal. So I think that is the point. So should this option? Is this one. Next, you will have to perform the tests. Using the software of your choice, conduct enough tests. So we go to Minitab. Remember, stat, ANOVA, one way. Now here we have to, for response, we have to choose new leaves. For factor is the treatment. And I think that's all. The rest I think is correct by default. So, okay. And there you have. The F value is 3.44. Well, what is asking for? F is 3.44. This one, see? And the p-value 0.031. 0.031. Use alpha equal to 0.05. So what are the conclusions? So do we reject H0? Yes. We reject H0. Why? Because the p-value is less than alpha. Reject H0. So we're saying that there is some effect, right? So the means are the effect for nitrogen, phosphorus is not the same. There are some differences. So here you have to choose the option nitrogen had a positive effect. The phosphorus and control groups were similar, and the plants that got both nutrients fell between the others. Well, here, notice in this case, we are not saying that, I mean, the right option is this one. This one. But here it said that nitrogen had a positive effect. How do we know that? Well, the conclusion formally should be only that that they are different, right? All the means populations are different, but in this case we're saying that nitrogen had a positive effect. How can we have methods to conclude that, right? But we don't see them here. But I think the book or Achieve is saying this to us because notice below in the results we got, the mean for nitrogen was the bigger. Yeah. So like I think that's where I'm saying that the nitrogen had a positive effect, right? But that's all. All right. So that's all by now. See you in the next video.